Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection. Today a theorem which is sometimes called Ramsey's theorem, I just call it the Ramsey numbers. And kind of the point is in the end that it really opened the field of combinatorics. It's kind of a nice counting problem with a really hard answer. So it's one of those counting problems where counting is really made difficult. So very simple in some sense counting problem comes under various names, very popular. Also on YouTube, links are in the description. So kind of a graph theoretical problem. You should count a certain number of things. We will see what it is. In the end, it turns out that the numbers are just ridiculously hard to get. Like for many counting problems, it's actually the case. So counting is not as easy as it usually looks like. And this is a really good example. But really the main point about Ramsey's theorem or Ramsey numbers is that they really opened a new field of mathematics, which is called Ramsey theory, which is kind of a subfield of combinatorics. I will elaborate on that a little bit, but basically what this subfield is supposed to do, it is kind of asking questions of the type, how big must X be such that Y holds? We will see how that works for the Ramsey numbers. There will be a structure X, and I will ask for the minimal n such that my structure X satisfies Y. And I'm going to explain X and Y, of course. That's kind of the point. But keep in mind, and that's very important somehow, is that this really triggered an old field of mathematics, which is called Ramsey theory, which is pretty exciting, right? If you prove a theorem, it's named after you, but actually what's really going on is some really new field of mathematics opened. That's pretty usually very rare and usually very exciting. So let's get started. So it's actually a very easy setup. So a certain type of graphs, and those graphs are usually denoted by k. So kn. So there's a number n, and the number n is the number of vertices. So here's k3, and I have 3 vertices, 1, 2, 3. And that's just very simple rule to connect them. Just connect everything without creating any types of loops or double edges. So just one edge per, just between two vertices, just one edge, and just connect everything. So a little bit boring is K1, it just has one vertex. So the one is referring to one vertex. And I need to connect it to everything else. Well, there is no other vertex, so it's a little bit boring. So it's just a vertex. K2 maybe is just this interval type thing. With 2 vertices, you draw a line between them, right? K3 is maybe the first exciting one. So I have 3 vertices, 1, 2, 3, and the rule tells me to connect everything. So I need to connect this one to both, and then I need to still connect those two. So which makes 3 edges and 3 vertices. The number of edges grows faster than the number of vertices. As you can see here, K6 has just 6 vertices, and we will see how many edges it actually has. Kind of the easiest graph you can imagine. Maybe not the easiest one. The easiest one is probably just a collection of vertices, but that's also a bit boring. That's a very important graph, and it turns up in many counting problems. Kind of this graph has all other graphs as subgraphs, if you want. Whatever all other graph means, of course. So it's kind of the point is those complete graphs, so they're called complete graphs, Kn, they're at the heart of many counting problems. By the way, I actually still don't know why those graphs are denoted K. That's not really C like complete. Maybe it comes from a different language. So Wikipedia says something like it might come from German komplett, but I have absolutely no idea. So if someone knows, I would be happy to know. Anyway, it doesn't really matter how you denote them, right? So whatever. Kn, the complete graph on n vertices, and a very easy rule, you just connect everything you see. And the problem here is that almost everything you count in Kn grows ridiculously fast. So here's my counting problem. I would like to color my edges. I would like to color them blue and red. 2 colors. In general, I could use more colors. If you can imagine more colors, blue, red, green, or whatever, blue, red, green, purple. But let's start with 2 colors. One coloring is also possible, but that's a bit boring. You will see. But anyway, I would like to color the edges. No restrictions on how I do that. So I just get through all possibilities. So how many possibilities are there? Well, I could decide for each edge. For example, I could decide for this edge whether it's blue or red. So I should get the number of possibilities should be 2 to the number of edges. So 2 to the number of edges. So it grows pretty fast. It grows with some power of 2. And let's count edges, actually. So Kn has these many edges. And you can see that by kind of very simple, in the following way. The way you count those edges on those graphs is you just write down your vertices and you connect the first to everything else. So if you connect the first to everything else, you get an n minus 1 because, well, as you can see here, I need 2 edges. And then you would connect the next one to everything else, but you already connected it to the first one, so you have 1 fewer edge, so you get an n minus 2. And then you get an n minus 3, an n minus 4, and so on, and you just sum them all up. And if you remember those funny formulas that you usually see very often, those little Gauss or whatever it's called, those are this many edges. It should be n times n minus 1 over 2. So n times n minus 1 over 2, check that for K4. 4 times 4 minus 1 over 2. 4 times 4 minus 1 is 4 times 3 over 2. So that's 12 over 2. That's 6. 1, 2, 3, 4, 5, 6. 1, maybe not blue. So 1, 2, 3, 4, 5, 6. Perfect. So usually it's very nice if you have a theorem like, well, the number of edges of Kn is something, and you should at least check it in one example. You should also check it for K5. I'm just very lazy right now, so it will work. Anyway, so this is the number of edges, and then of course I get this ridiculously huge number of blue-red colorings of the edges, right? So let's check that for K3. So here's K3. And K3 has 3 edges, so I expect 2 to the 3, which is 8 colorings. And yes, of course, I get 8 colorings, very simple. So everything blue, everything red. It's kind of the 2 extreme cases. And then I have 1 edge colored blue, so red in this case, of course. And here's the 1 edge colored blue case. And there are 3 possibilities of them, of course, because the edge just moves around. So really, you have just those 8 possibilities. And this was kind of the last one that fits on the slide. So the next one has already pretty many colorings. I probably could have fit it on the slide, but it would be very tiny. The point is those numbers grow ridiculously fast, right? It's 2 to a big number. And this is kind of where the heart of the problem lies. So here comes now the problem. Remember that we wanted something like how big must the structure X be such that Y holds? Okay, my structure X is now Kn. So how big must X be to guarantee that Y holds? So X is Kn, and Y is the following. It's actually this property here. Kn contains, so this one, contains certain subgraphs, and I will explain that in this example here in a second. So I have this number here, which I call, or which people usually call R, blue-red, right? 2 colorings, blue-red. And so what's the smallest n such that Kn contains either a blue Kb or a red Kr? So let's have a look at an example. So what is, for example, R33? R33 would ask for the smallest n such that I have either a blue K3 or a red K3, right? So either a blue or a red. I'll show you a nice Mathematica animation in a second. But if you remember what K3 is, so here's K3, this just means you have a triangle of a fixed color. Okay, so what is the smallest n such that this is possible? And the way to attack this problem is actually not so simple. So simply counting or listing all possibilities is not a good idea. They grow very fast. Of course, for K33, you could still list everything. It just should work. For R33, we'll see that. But the better way of doing this is to kind of somehow get an upper bound. I will tell you about that. And that's kind of the Ramsey theory or theorem. And then kind of rule out lower cases, which is still ridiculously hard. I will comment also on that in a second. Let's have a look at the example. So I claim that this picture here shows that K33 is not 5. It's at least 6. So how can we see that? The point is, what is the smallest n such that xy holds? Okay. In order to rule out a certain n, you just need to find a coloring where this doesn't hold, right? So here's a coloring where there is no red triangle nor a blue triangle. So let's have a look. Whatever. Here's a red edge. Here's another red edge, but the last edge is blue, so this is not a red triangle, right? And it's also not a blue triangle, of course. Similarly, whatever. Here's a blue edge. Here's a blue edge, but the remaining edge is red. So this is also not a blue, neither a blue nor a red triangle. And as you can see in this example, this coloring of K5, which is this kind of funny, whatever it is, pentagonal graph, this doesn't have any colored triangle. That's kind of where the idea comes from. So this problem is also sometimes, this is called the Ramsey problem, also sometimes called the party problem. So here comes a way to remember it. At least for some people that actually works. So imagine that you're at a party and each vertex is a person. So person A, maybe person B, person A, person C, person D, and person E. And you kind of draw an edge between them always, and you give it a color depending on whether they know each other or whether they don't know each other. So red could be don't know, and blue could be, for example, do know. So don't and do. And then the Ramsey number asks kind of for the smallest party, in this case here, where you will find a triad of people such that everyone either knows one another, so a big friend group, or they're completely strangers. In this triangle, nobody knows anyone, kind of completely disjoined. It's kind of called the party problem. I'm not sure whether I really like that, but anyway, it's very popular. It's called the party problem. I can personally remember it a little bit better in the abstract formulation. So this RBR, very hard to pronounce, RBR, asks for the smallest possible complete graph, which contains a certain colored subgraph, either blue or red, and whatever kind of number you see, that's what you're looking for. So you can also ask for R2510. I will give you more examples in a second. And what I said is that this picture shows that R33 is not 5 because I found the coloring, or someone else did it actually. Of course, I copied it from somewhere. Links are in the description. Found the coloring where there is no blue or red triangle. So let me have a look at Mathematica and at the next one, so K6. So here's K6, and what this demonstration does is you can choose one of the colorings, and there are quite a few colorings, so you should do that by hand. So here's the all red coloring, here's the all blue coloring, and kind of everything in between. And the point is now that I claim, or whatever Ramsey theorem claims, in this case, that R33 should be 6. So for all colorings, I should be able to find either a blue or red triangle. And the way how this is indicated here is, well, let's have a look at the easiest case, is whenever you have a blue triangle, you get a blue circle around the corresponding edges, vertices. And whenever you have a red triangle, you get a red circle around the corresponding vertices. So here, for example, this has a blue triangle here, as you can see. So it goes around like here, and a red triangle here. So this one is good. It contains either a blue or a red triangle. I would be already happy if I just found a blue or a red, but this actually has both. There could be, well, this one is very good. It has no blue red triangle, has quite a few blue triangles. And you kind of can see the problem here. This one has just one blue triangle and quite a few red triangles. Kind of, you can see the problem, because the redder your graph gets, the more likely it is to get a red triangle. The more blue you have, the more likely it is to get a blue triangle. But of course, the more red it is, the more unlikely it is to get a blue triangle. And the more blue it is, the more unlikely it gets to get a red triangle. Cool. And that demonstration actually shows, because it goes through all cases, that R33 is 6. Which is really not a good way of showing this, because the number of cases is just ridiculous. Of course, you can do that with a computer, but Ramsey theory by now is something like, or Ramsey theorem by now is whatever, 100 years old, and for 100 years ago, the computers weren't very fast, to say the least here. And now enter the theorem. A bit surprising in my opinion. So the main theorem in theory, and that's usually the main theorem in Ramsey theories in general, is that the problem actually has a solution. And that's not quite obvious. I mean, why should this number even exist? So this number always exists, which means it is finite. And the way to prove that is to find an upper bound. So here's some upper bound, which actually works pretty well. So let's see b equals 3 and I equals 3. So then you get something over 2. So it's 4 over 2, and 4 over 2 is 6. So this actually tells you that R33 cannot be worse than 6, since this picture actually already shows, so just this one, that it's not 5, we're done at this stage, right? It's not 5, it can't be bigger than 6, so it needs to be 6. And that's usually how you prove whatever those numbers are. Actually very nice, right? It's not quite clear why this number should actually exist, so why this should be a finite problem at all. But kind of the point of all Ramsey theory, of all of those theorems, is that they're actually usually finite, which is a bit surprising. And the same works kind of for any number of colors. I'll show you an example in a second. So let's go through the table here. It turns out that those numbers are, counting is impossible. They're ridiculously hard to compute. So here in this table, so blue goes in this direction, red goes in this direction. I've kind of marked in green where we know the numbers. There's some trivial cases. We will go through that in a second. So for example, if blue is 1, so you need to find a K1. You will always find a K1 because K1 was a boring one here. So there's no condition on the edges. So they should be satisfied all the time. So it's just K1 all the time. So here it's just K1. And the way how this table works is actually here's also just 1. But because of the symmetry, I kind of don't bother to write down whatever is below the diagonal. So it just takes this picture and flip the numbers over, and you get whatever is below the diagonal. So anyway, so the first, row is kind of clear because you count K1. Counting K2 is also not so hard. So how can you find K2? Well, you at least need to be in K2. So B22 should be 2. And yeah, of course it is. No matter how you color your edge, you will always find a red or blue edge. So that's what it is all about. So the only restriction here is that your graph needs to be big enough. So that's what it is. So those numbers are 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And the next column, or row, sorry, the next row is already not so trivial. So here was our K33, which wasn't quite easy. And the other ones are much harder. And as you can see, it breaks down at one point. So I stole this table from Wikipedia 2021. And apparently, this is R310. R310 is still not known in 2021, which is kind of weird. You think you should be able to do that with a computer, but the numbers grow really fast. And that's not really a good way of doing it. It's kind of a disappointing point here. So there's not really a kind of you write down a formula or something like that. It's not as easy. And so here are other numbers. So the diagonal is, of course, kind of the main point. K55, R55, R66, and so on. Usually get bounced very easily, but that's about it. And then there's just really no good way of checking this. And already those bounds are, some of them are actually pretty good. So that this is 43 and 48 is not quite trivial. There's some very nice links on the Wikipedia page. Anyway, so this is a huge table, and there's a very simple counting problem. And apparently, the solution is just hard. It's just not easy to find. Kind of the best thing you can prove about it is the Ramsey theorem itself, which says the problem is finite by giving it an upper bound. Obviously, there's a lower bound anyway, so K1 is certainly a lower bound, but the upper bound is the main meat here. And just to make me clear here, already this one actually might be solved at one point, maybe in my lifetime, who knows? But this one probably will never be solved, or at least we would need very different methods right now. We don't have the good tools to attack that problem. That's what you should say, right? It's kind of a hopeless counting problem. Okay, let me show you. Oh, this is complicated, but really hopeless counting problems. You can do the same for 3 colors. So my colors here are red, as before, blue, and I have a third color, green. So you can ask exactly the same question. So something like R333, and it's kind of not so hard to see that it's not bigger than 17. So to find those upper bounds is usually not so hard. Here's an illustration that it's actually, so this is 16. So this is a case 16 that you see here, well, which is hard to see. And this case 16 has no, again, it asks for a red triangle, a blue triangle, or a green triangle. And if you stare on those pictures long enough, you can convince yourself that this case 16, so the 16 vertices, here are 5, here are 5, here are 5, and here's one in the middle. Same here, 5 vertices, 5 vertices, 5 vertices, one in the middle. This case 16 has no red, blue, or green triangle. So as soon as you know the upper bound, it's then not so bad anymore. You still need to check all of those possibilities, or you need to be smart and write down a counterexample like this one here. And kind of the real problem here, the real meat why this is so hard, is that this case 16 has just this ridiculous number of red, blue, green colorings. You don't want to write them down on paper. Nah, you definitely don't want to. So before I said it was 2 to the number of edges, right? And that's, of course, in general, it should be the number of colors to the number of edges. So in this case, 3. And this is it just grows too fast. 2021, we all had a pandemic behind us. Some numbers grow very, very fast. So exponential growth is extremely scary. Here's another example of very scary exponential growth. And that's the problem is that there's this ridiculous number of possibilities, and almost all of them are good. And up to symmetry, there are only those two where you don't find any reasonable or any blue triangle, red triangle, or green triangle. Anyway, let me wrap up. So Ramsey theory is kind of this idea of counting or kind of measuring how big a structure X must be that such that Y is satisfied. And it's based on Ramsey theorem, which is saying that a certain counting problem involving complete graphs kind of has really an upper bound. So it actually is a finite problem, and then it kind of only remains, only in huge quotation marks, remains to figure out what the precise numbers are. And combinatorics is sometimes really a mean beast, and in this case, it is a mean beast. So it's really, really hard to figure out those numbers precisely. Usually you get nice bounds, but to figure out those numbers precisely is very, very often very hopeless, which I find a bit surprising because it looks like combinatorics, yeah, you just count, you just feed it into a machine, you're good. But actually, some numbers just grow so ridiculously fast or are so complicated and so random that even a machine can't help you. Anyway, I hope you enjoyed the video, and I also hope to see you next time.